All right, so what we're going to look at in this lesson is two other methods on how to solve quadratic equations. We've already looked at two, one being graphing to solve for the roots, and the other being solving by factoring. So today we're going to look at solving using completing the square and solving using the quadratic formula. So in this method 3, in solving using completing the square, right, this one uses that more traditional form of algebra where you're just kind of like getting x by itself. Because when you're in vertex form, in this form of y is equal to a times x minus p squared plus q. So if we gave an example of, let's say, y is equal to 2 times x minus 3 squared plus 7, right? And we were then asked about what are the roots of this equation. We would have set y equal to 0 here, 0 equaling 2 times x minus 3 squared plus 7. What you should note is that there's only one x. There's only one time that the variable actually shows up, right? And it's right here, right? Whereas when it's in standard form, right, if we were to compare it to a y equals, let's say, 1/2 x squared plus 5x minus 3, right, we see that the x shows up in a couple different terms, and one with an exponent of the 2 and the other with an exponent of 1, so they can't be combined and you're forced to kind of factor, use the quadratic formula there. But in vertex form, right, which we can get to through completing the square, we only have one occurrence of that x variable, which means we can just algebraically undo all of our operations to isolate x and get it by itself. All right, so just one thing to note as we go through this, remembering that when we do square root stuff, there's always two possible answers, a positive answer, right, and an equal but negative answer as well, right, and that's how we're going to get those two roots potentially out of an equation. All right, so let's start with a simple example here. So given this quadratic equation, x minus 1 all squared minus 49 equals 0, again, we're essentially looking at a concave up parabola that we know has vertex at the point 1 and negative 49, right? And because that vertex is underneath the x-axis and it's concave up, we know there are going to be two real roots to this, right? So let's try and take a look at how we would solve it. Starting by setting the equation equal to 0, right, because we're trying to solve for when does the function cross the x-axis. So what we have here is x minus 1 squared minus 49 equals 0. Okay, and again, because there's only one occurrence of this x variable, we can just start isolating x. So the first thing we're going to do is add 49 to both sides. Right, so we're going to get x minus 1 squared is equal to 49. We're then going to square root, right? In order to get rid of this squared aspect here, we need to square root both sides, right? Because essentially what we're doing here is square rooting x minus 1 squared and square rooting 49 at the same time, right? So square rooting something that's squared is essentially going to cancel those operations out, and you're just going to be left with x minus 1 equals, now there's two options here, either plus or minus 7, right? So the square root of 49 is 7, but it can also be interpreted as negative 7. Right, that now gives rise to two separate equations where x plus 1 is equal to 7 or x minus 1 is equal to negative 7. Sorry, I said x plus when I should have said x minus over here. All right, so then we're just adding 1 to both sides to get x by itself. So x equals 8, or adding 1 to both sides here, and x equals negative 6. Okay, and we've now solved for those x-intercepts. And again, you can always go back and verify, right, is this the correct answer? You can graph it to try and check it. You can also verify it algebraically by substituting those values back in your equation, right? 8 minus 1 squared minus 49. Does it in fact equal 0? Well, that's 7 squared minus 49. Yes, so 49 minus 49, it does equal 0. You could do it with the negative 6 as well. Negative 6 minus 1 squared minus 49. Does it equal 0? Well, that's negative 7 squared minus 49 equals 0, and once again that's positive 49 minus positive 49 equals 0. So yes, it does work. Okay, so what that kind of leads us to an example of is how we complete the square again, right? So if something's not in that vertex form, right, as we see here, x squared minus 21 equals negative 10x, it's not in vertex form, and if we're going to use this method of solving by completing the square, we will have to put it into that vertex form, okay? So again, what we're going to do at that stage is first start by bringing everything over to one side, so x squared plus 10x minus 21 is equal to 0. And now we're going to go through our method of completing the square, right? So we start by bracketing off our terms that contain the variable x. We then find that number that's going to create a perfect square quadratic, which is half of 10, right? So we take that b value, 10, divide it by 2, that's 5, and then we take 5 and we square it. Right, so 25 is the number that we both add and subtract, essentially adding 0 inside that set of brackets, and then the minus 21 equals 0. Right, we then kick the negative 25 out, so we get x squared plus 10x plus 25. Oh. There we go. And then minus 25 minus 21 equals 0. We now have that perfect square quadratic that factors into x plus 5 all squared. We can combine our constants, negative 25 minus 21, negative 46 equals 0. And now we're back at that same stage that we would have had in that previous example, right? So now it's a matter of trying to isolate that variable of x, so adding 46 to both sides. So we get x plus 5 squared equals positive 46. We then square root both sides, so that's just going to leave us with x plus 5 equals the square root of 46, remembering that there's both a positive and a negative answer here. Right? So that sets us up with those two equations. X plus 5 equals positive root 46, and x plus 5 equals negative root 46. Right? And we're going to get in the habit of leaving our answers as exact answers. Right? When it's not in context, if it's something's asking for exact answers, we're going to leave these as radicals, right? So what we're going to write here is now x is equal to root 46 minus 5, or here, negative root 46 minus 5. And we can try and simplify that radical and ask ourselves, okay, is 46 divisible by any perfect squares? Is it divisible by 4? Is it divisible by 9? Is it divisible by 16? Is it divisible by 25? No, it's not. So this is as simple as it's going to get. Right? So these would be our exact. Right? These are our exact values. Okay? Right? No rounding errors have occurred. Right? Again, you can always get an approximate value by doing, calculating on your calculator the square root of 46 minus 5 and saying that that's approximately equal to 1.78, or that this one is approximately equal to negative 11.78, right? But exact values are something we're going to keep in mind, okay? So we'll just do one final example on this, on the completing the square, okay? So again, this is one where you do have a coefficient in front of your x squared term. So once again, you can just factor out that 3. Okay, we're actually going to leave the 8 over here on this side for right now, just to kind of show you that it works in this way as well, right? You don't have to have that 8 over there and set equal to 0. You can instead just start by saying, okay, my x terms are on the left-hand side. That's great. I'm going to start by factoring out that 3 of my x terms. So I get 3 times x squared plus 4. Let me just leave that 8 alone over there on that right-hand side. Okay. Sorry, that should be 4x. Okay. And then what we're doing is once again trying to figure out what is that perfect number that we need to add to make that a perfect square quadratic. So it's half of the b value. So the b value right now is 4. 4 divided by 2 is 2. And 2 squared equals 4. So we're going to be adding and subtracting 4 inside that set of brackets. So 3 times x squared plus 4x plus 4, but also minus 4 equals 8. All right, we don't want this negative 4 here, so we need to kick it out. But since there's a factor out of 3 here, the 3 is going to come in and factor, like the 3 is what's going to help us kick out that value of negative 4. Sorry, go back here. There we are. Okay, so again, it's the 3 that's going to come through and take out that negative 4. So you're going to have 3 times x squared plus 4x plus 4, and then minus 12, since 3 times negative 4 is negative 12. Right, and then it still equals 8. Right, then we can factor this into a nice perfect square quadratic, so it's just x plus 2 all squared, and we can actually take this negative 12 and bring it over to the other side, right, to combine it with that other constant 8 by adding 12 to both sides. So now that equals 20. All right. So again, now we've got something that we can try and isolate x. There's only one occurrence of that x variable, so then we'll start by dividing both sides by 3. So we'll have x plus 2 squared now equals 20 over 3. We're going to leave that as a fraction, right? Now we're going to square root both sides. So we get that x plus 2 is equal to the square root of 20 over 3, remembering that there's both a positive and a negative answer. That sets up two possible equations here where x plus 2 equals the square root of 20 over 3 and x plus 2 equals the negative square root of 20 over 3. And then once again, isolating for x by subtracting 2 from both sides. So root 20 over 3 minus 2 and negative root 20 over 3 minus 2. The root 20 can in fact be simplified since it can be written as 4 times 5. So that's actually 2 root 5 over 3 minus 2. Same thing over here. It's negative 2 root 5 over 3 minus 2. And if we wanted to be really concise here, we'd actually combine these terms, right? So we could get a common denominator here, rewrite 2 as 6 over 3. And then we can actually rewrite this whole thing as one big fraction of 2 root 5 minus 6 over 3. And the exact same thing would happen over here, where you have negative 2 root 5 over 3 minus 6 over 3. And then you get negative 2 root 5 minus 6 all over 3 as a single value, right? And we have exact fractions, okay? And I'll stop there, and in the next video, we'll do solving using the quadratic formula.